Hey, we're going to solve group whiteboard problem 10.5. So we have a wooden block slides down an incline. Okay, just sketching this on my paper. Okay, the coefficient of friction, kinetic friction is 0.05. The angle of the incline is 30 degrees. The mass of the block is 2 kilograms. Use conservation of energy to find the speed of the block at the bottom. So that's what we want to find. V final. And if the block starts at a height, so y initial is 0.5 meters. Okay, so let's check this out. This one's a little more involved, so be patient. Okay, so here's theta, here's our block. Okay, so the block is starting at a height. This is y initial. It's going to slide down at the bottom. We're going to have some speed here. And there is friction, so we're going to lose some energy on the way down to thermal energy. So let's do our energy bar charts. Okay. All right, so initially we have gravitational potential energy. We'll put in kinetic here just for completeness, even though we start for rest. And then at the end, we have gravitational final potential energy, kinetic final, and we have some energy that's going to be lost due to friction, thermal energy. Okay, so we actually have the double diagrams that we need here, right? So this is just our sketch of what's happening. We want to also do our free body diagram because if we want to figure out the thermal energy, this is going to be equal to delta E thermal is the force of friction dotted with the displacement. In this case, they're going to be in the same direction. But okay, so let's look at our free body diagram. So we have force of gravity going downward. And let's just sketch in the plane, which will also be our x-axis. Then we have the normal, that'll be perpendicular to that. And then we have some force of friction that's slowing us down. Okay. So remember, if we just want to look at gravity by itself, right, and what its components are, we have a component down the incline and then one perpendicular to it. Gx, gy. And I'm going to set up my coordinate axis to say that is positive x and this is positive y. Okay. And remember, inside the gravity triangle, that's perpendicular. This is theta. Okay, so let's look at the energy bar chart and then we'll worry about figuring out this thermal energy. So initially we have all of our energy as gravitational potential energy. Initial kinetic energy is 0. At the bottom of the incline, I'm going to have no gravitational potential. I'm also going to have kinetic, right? My block is moving, but it's not as much as I start with in terms of gravitational potential. So there's a little bit, actually I don't really know until I do the calculation how much is going to get lost here to thermal energy. Okay, so let's write out our conservation of energy equation. So we have UG initial plus K initial equals UG final plus K final plus delta E thermal. Okay, and then right away we'll get rid of things that we know are 0. So starting from rest, there's no kinetic energy. It ends at the ground, so there's no potential at the end. Okay, and then, so let's put in our equations here. So mgy initial equals 1/2 mv final squared plus the force of friction times delta x. Where delta x is how far this travels down the incline. Okay, so let's quickly relate that. So I have confusion here. Maybe we should say that this is, maybe we should call this height initial. because otherwise I'm going to have two y coordinate systems. Gravitational potential energy just cares about how high I am above the surface of the Earth, right? But when I do my free body diagram, I'm setting up a different coordinate axis. So I'm going to just change that to height so we don't get confused, okay? Okay, one more little bit of geometry. So it tells us this length, right, is 0.5 meters. That's the height. And I need to know, for friction, I need to know how far it travels. Okay. So this is my opposite side. This is my hypotenuse, right across from the 90 degree. So if I do sine of theta is the opposite side, which would be my height, divided by my hypotenuse, delta x. So if I just want to figure out what exactly the distance that the block travels, it is h divided by sine theta. So that's going to be useful in a minute. Okay, so now we have our energy equations set up here. We need to get this from a force analysis. Okay, so this is a biggie. All right, so let's take a look at our free body diagram. So we're going to do sum of the forces equals ma. All right, and then we have the forces that we're looking at. We're going to put in, let's say, the normal. We'll make space for that. Force of gravity, make space for that, and the force of friction. Okay, and that equals max and may. Where there is no y acceleration, right, my block is not going to accelerate up off the plane. All right, so my normal is in positive in the y direction, f normal, and it has nothing in the x direction. So remember, I'm keeping track of my x and y components of my forces. And then I have force of gravity. So it's going to be, the way I set it up, it's actually going to be positive fgx and minus fgy. And then my force of friction is negative in the x direction and 0 in the y. Okay, so if we look back up here at my gravity triangle, right, x is the side opposite the angle. So this is fg sine theta. This is the adjacent side, it's fg cos theta. Okay, so if I rewrite this one more time, so I have 0 fn, and then here I'm going to say that this is fg cos theta, and this is minus, no, I did that wrong, fg sine theta, and this is minus fg cos theta. Okay, and then my force of friction is minus mu times the force of the normal. 0 equals max and 0 here, right? Ay is just 0. Okay, so I don't really need to solve this. I just need to know what this value is. And which means I need to know the normal. So that comes from my y equation. So the y equation, if I just break out this line, it says f of the normal minus fg cos theta equals 0. So force of the normal equals fg cos theta, right, which is mg cos theta. Okay, so I have that now. I have my delta x, and I can keep going in my conservation of energy equation. So let's do our algebra first. We want to solve for v final, so we need to get this by itself. So we have mg, so I'm going to bring this down now. So I have mg, initial height, equals 1/2 m v final squared. My force of friction is mu times the normal, which is mg cos theta, and then times my distance traveled, right, delta x, which we said is h over sine theta. It's delta x. Okay, we do have a mass in every term, so that goes away. We want to multiply through by 2 to get, because we're trying to get v final by itself. So if I do that and subtract this term, I get 2gh initial minus mu g cos theta h over sine theta equals v final squared. Okay, I'm going to take the square root of both sides. And then we may have to break quick and let my dog in and flip over to the next page. So we have v final equals the square root, oh boy, of 2g h initial minus mu g h over tan theta. I'll give you a minute to think about how I did that. Let's see. Okay, just magically pause that for a second. The dog came in. Whew. Okay, this is a long problem. So I think we're ready to plug in now. So we have the square root of 2. G is 9.8 meters per second squared. Of course, now she's drinking. She's not cooperating for our filming. 0.5 meters is our initial height, and then we have mu 0.05. Oh, gee, again, I could have factored one out. 9.8 meters per second squared. My height. Goodness, you guys, we have a G and an H in both terms. I'm very disappointed in myself. I'm going to blame it on the dog. 0.5 meters, and then tan of 30 degrees. Does this work? Can you see her? There she is, see? The little tail going. This is all about her. Okay. Now she's hitting me. All right, so let's open up our calculation window. And I guess I'm just going to type all this in. MP square root. So we have 2 times 9.8 times 0.5 minus 0.05 times 9.8 times 0.5 divided by the tan, and just forgive me here, and just convert that into radians for 30. Okay, V final is 3.06 meters per second. Okay, let's just quickly review, make sure we have all of our presentation points, right? We have what we're given, what we need to find. We have our sketch. We have energy bar charts. In this case, we also have a free body diagram because we have to deal with friction. We have our general conservation of energy equation. We have our general force equation. We solve for the normal. We then plug into our conservation of energy equation, solving for V final, doing our algebra first. And I goofed up a little bit. We could have done even more algebra. We could have factored out the G and the H in here, right? This could be the square root of 2 of GH, 2 minus mu over tan theta. But, we'll save that for another time. Okay, we plugged in our values and then boxed our answers. We have our labels, units clearly labeled. I'd give myself full credit for presentation.